Good afternoon, everyone, and welcome to this joint EOL seminar with M Cubed. It is my pleasure to introduce our speaker, Dr. James Doyle, who is an EOL affiliate scientist. After receiving his PhD in meteorology from Penn State, Dr. Doyle joined the U.S. Naval Research Laboratory in the Marine Meteorology Division in Monterey, California, where he is now a senior scientist. Jim is one of the lead scientists for the Mesoscale coupled system COAMPS and the next generation model Neptune. Dr. Doyle directs the developmental team for NRL's operational COAMPS-TC tropical cyclone model. Jim's research interests are impressive in both topic and in breadth, including Arctic meteorology, tropical cyclones, topographic flows, high impact weather, and mesoscale predictability. In his presentation, Dr. Doyle will address research in the realm of Arctic meteorology. It is titled Arctic Cyclones and the Influence on Short-Term Sea Ice Change and Moisture Transport. As a nod to Jim's topic, my background screen is an image, courtesy of NASA, that depicts a mosaic of MODIS satellite images showing a massive low pressure center spinning across the central Arctic Ocean. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Do not be alarmed if you do not see your question. We are archiving all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Dr. Jim Doyle, we welcome you to NCAR, and the virtual stage is now yours.
Okay, thank you very much for the kind introduction. Just a mic check, you can hear me okay?
Yep, we can hear you just fine.
Great, thanks so much. I wish I could, of course, be there with all of you in Boulder and experiencing the 2 feet of snow that you've gotten there, but it sounds wonderful. But nevertheless, it's great to be here virtually as well. And thanks so much to NCAR for the invitation to present. This is always a great opportunity to connect with so many of my colleagues and friends at NCAR. And I'd like to thank my co-authors listed here, Pete Finocchio, Dan Stern, Matt Fearon, who worked with me closely on this material today. And all 3 of them have led 3 different papers that have recently appeared in the Geophysical Research Letters. I'd also like to thank Neil Barton and Joe Metzger, who is at NRL in Stennis, Mississippi, and our oceanography expert. I'd like to also acknowledge the sponsorship of the Office of Naval Research as part of an Arctic Cyclone Initiative. So when I grew up in Wisconsin, and the so-called frozen tundra of Wisconsin in the winter, it can be quite dramatic when I grew up. And I always wondered about the Arctic and what it was like. And this project has been a great opportunity to learn more about the meteorology of the Arctic. So the outline for this talk is begin with a brief background and talk about a coupled modeling study of an Arctic cyclone, have a bit broader of a perspective through reanalysis, taking a look at many years of Arctic cyclones and sea ice loss. The third topic is Arctic cyclones and their role of transporting moisture into the Arctic, and then end with the summary. As I mentioned, Pete Finocchio, Dan Stern, and Matt Fearon all led papers that are summarized in this presentation. And so the references are here in case you want to read more about the details. A little bit about the Arctic. Of course, all of you are aware that the Arctic is changing, and we live in a time of rapid change in the Arctic. The Arctic sea ice extent is in rapid decline. As you see on the right, there's increased air temperature, multi-year sea ice loss. The mean thickness is reduced. We see changes in the upper ocean, amplified ocean acidification, accelerated melting of the Greenland ice sheet, warming of the permafrost, changes in the balance of all sorts of very delicate processes in the Arctic, and new feedbacks. And we also see, as I mentioned, changes to the thickness. And so we see thinning of the sea ice. And this thin sea ice may be more vulnerable to atmospheric and oceanic forcing. And one of the topics we're looking at is Arctic cyclones, and that is an atmospheric phenomenon that may be having greater impact due to this thinning sea ice. At least that's a hypothesis. So along those lines, the Office of Naval Research has an initiative that seeks to quantify the influence of Arctic cyclones on sea ice and identify sources of sea ice predictability. You can see on this graphic to the right, this dramatic graphic from Zach Labe, by decade, showing the sea ice dramatically thinning until the most recent decade. So very dramatic changes are going on. So we're focused on these Arctic cyclones. These aren't the little tiny little polar lows that have a different structure and much smaller size that tend to form over open water. These Arctic cyclones are synoptic scale baroclinic waves that we're most interested in. And these have been hypothesized in the literature to impact sea ice loss in part because of strong surface winds. An example is shown here, an intense cyclone with a central pressure of 975 hectopascals passed through the marginal ice zone in 2020. And here we mean the marginal ice zone of somewhere between 15 and 80% sea ice concentration. And this is in the Beaufort Sea. This is a series of NASA images. And you could get a sense of, through this period, you could get a sense of the thinning of the sea ice in almost in a circular fashion, where this particular cyclone, which had very slow movement, and you could see a number of places have thinned in the sea ice. And this is also magnified or further reinforced by some analyses that come out of NSIDC. And you could see with time, over this time period, the sea ice has thinned in this period, and certainly looks compelling that the cyclone may have played a role in this. If we look at another example, and this is a more well-known example, sometimes called the Great Arctic Cyclone of 2012. This occurred in August of 2012 and was correlated at least with a significant reduction in the total sea ice extent and volume over the course of 5 to 10 days. So these are the ERA 5 winds and sea level pressure during the peak of the intensity of the cyclone. And this is the cyclone track. It's kind of a complicated track, slow moving into the Arctic. And we see on the right panel here is a plot of the sea ice extent on the y-axis, the date or the time on the x-axis. We can see there's a period where the kinetic energy here in the dotted line increased dramatically as that storm intensified. And at the same time, in these warm colors, the red and orange, there's a rapid decline in the sea ice extent, and also the sea ice extent anomaly went down in the blue. And it certainly looks compelling that that storm had a significant impact. And so we're asking questions in general, what are the key processes, the coupled processes that lead to these sea ice loss events during these intense cyclones? How much of a short-term change in sea ice can be attributed to cyclones in general? And how do cyclones influence moisture transport into the Arctic? So we'll be considering all three of those. One of the models in the first part of the study that we'll be using is a fully coupled model developed at the Navy called the Navy Earth System Prediction Capability, ESPC. It includes an atmospheric model, NavGem, an ocean model, HICOM, and an ice model, SICE, the community model. And these are some animations. The future would like to include waves. That's not quite fully coupled yet. These are some animations of the HICOM salinity. Here you can see nicely the very strong gradients and eddies along the Gulf Stream. You can also see in the animation to the right, the sea ice thickness for one of the simulations or forecasts. This model is operational now, and it runs in 2 different modes. And the ensemble mode has been operationalized. It runs out to 45 days. It's fairly coarse in the atmosphere, 37-kilometer resolution, but fairly high in the ocean, 9 kilometers for the HICOM ocean and 9 kilometers for the sea ice. And there's a deterministic version that's about 4 kilometers for the ocean and ice. And the deterministic version isn't quite operational yet. They're still working on that. Nevertheless, we used this version, one of the members, the control member from the ensemble system, and this member we used to diagnose the coupled modeling study of this particular cyclone. So the cyclone we're looking at is indeed this great Arctic cyclone of 2012. And this is just a comparison at the peak intensity time of the surface wind fields and the sea level pressure, comparing the Navy's 36-hour ESPC coupled forecast on the left and the ERA interim reanalysis on the right. So this forecast basically captures the analyzed wind field structure. In particular, note that the strongest winds are found in this elongated region in the warm sector of the cyclone, and these warm colors that begin near the coast of Alaska and extend northward to the north of that cyclone. And you see a similar looking structure in terms of the low-level jet and the warm sector of the reanalysis cyclone too. So in this band of strong winds, these wind speeds are in the range of 15 to 20 meters per second, just ahead of the surface cold front. So a little bit more about these coupled simulations and what they have shed some light on. So the cyclone causes locally enhanced melting of the sea ice, both from above and below, and I'll talk more about this. So this slide shows how the surface melting is enhanced, associated with increased sensible heat flux, associated with the warm air advection by the cyclone. So here on the left figures, we see, first of all, the surface melting rate, and we can enhance that a little bit so you can see that a bit better. So this is occurring in the warm sector of the cyclone, and if we look at where the temperature near the surface is, you can see this warm sector as the southerly winds bring up relatively warmer air from the south. So these strong winds are brought poleward basically from Alaska out over the open ocean. The right figure now shows a time series of the total energy flux into the ice. And first of all, on the rightmost figure, we could see a comparison of the total energy flux in the surface ice melt in the red. You can see they're well correlated, and the energy budget that we're using is able to capture that really strong period of surface ice melt. So if we look now on this left panel, the second panel from the right, we see the various components of the energy budget. So this compares the components, and note there is a different axis, the energy flux here in red versus on the right axis associated with the red lines, we have positive and negative values. So looking at the different components, the absorbed shortwave radiation is the largest forcing, and that's in this dashed line with the filled dots that you'll see there. And so that seems to have a very big impact. In contrast, the time variation of the sensible heat flux really does correlate, and some of the other components do not correlate. You could see, for example, this dashed line of the absorbed shortwave. And so we see the sensible heating really does correlate with the total fluxes, and that we think are really important for driving some of the changes in the surface melting. Now, if we take a look next at the ocean processes, we could see in a similar view of the cyclone, the sea level pressure shown in the black contours again. We have the ice bottom melt here on the left, and we also have enhanced sea surface temperatures in this region too, where this warm sector and the very strong winds were located. So the enhanced bottom melting occurs where the SST has increased beneath this region of strong winds. Now, if we take a look at the latitude depth cross sections, and this is between 0 and 60 meters in the ocean, and this first figure on the left, second from the right, is the ocean temperature above freezing, and we could see some regions of a subsurface warm layer that exists 15 to 25 meters below the surface. And on the right are the 24-hour temperature changes. You could see during that 24-hour, I'll zoom on this, during this 24-hour period, we could see that a cooling occurs a little bit deeper below the surface and substantial warming. And this implies that there was storm-induced mixing that occurs associated with the very strong winds on the surface. So this is turbulent mixing in the ocean boundary layer that basically results in enhanced melting by warming the surface and bringing these warmer temperatures in the ocean boundary layer up near the surface. So we enhance the melting from below as well as a result of this cyclone. Although the melting is substantially enhanced by the cyclone in the coupled system, this effect overall is, in this model at least, is local and transient. This figure shows the time series. This is through the entire month of August 2012 of the 24-hour ice volume change integrated over the entire Arctic. And so negative here means a loss of ice. Each colored line is a different Navy ESPC simulation, initialized at different dates. You can see that there's no clear signature in this trace of the cyclones as it marched along. In contrast, the ocean ice model biomass, which is used frequently in the community, that's forced by a reanalysis, predicted enhanced sea ice melt associated with the cyclone. So we're still trying to sort this out, why the Navy ESPC is different from the biomass analysis. Dan Stern has been leading this work, and he has done a number of follow-on simulations working with our ocean and coupled model colleagues. And have forced the model with other atmospheric forcing other than the Navy atmospheric model. So we've used reanalysis and NCEP reanalysis, and also the ERA interim reanalysis. And so we're unpacking those results now, trying to understand this a bit better. So let's shift gears a bit now and take a little bit of a broader perspective, a reanalysis perspective of Arctic cyclones and sea ice loss. This is some work that Pete Finocchio has led. And we're taking a look at Arctic cyclones in the ERA 5 reanalysis from May to August over a 20-year period. And we've looked at selected a subset of cyclone cases that have a minimum central pressure less than 1,000 millibars, last at least 48 hours, and are within 500 kilometers of the sea ice edge. The changes in sea ice extent are then computed around the cyclone within a 500 kilometer radius for 1 to 5 days after the passage of the cyclone. So we can see the different months here shown for May, June, and July, August that we're concentrating on. And these solid dots show the different cases of the cyclones. And these are actually denote the wind speeds, the maximum 10-meter wind speeds in these events. And interesting, you could see how the cyclones shift with time. So cyclone cases are most frequent in a fairly narrow marginal ice zone in the Atlantic sector in the May to June timeframe. And then they sort of shift to the broader marginal ice zone of Siberia and Alaska in the July to August time period as the sea ice thins. So we'll take a look at some cyclone distributions just to orient you with some of the notation used here on these box and whisker plots, the analysis that Pete did. So the distributions are expressed in terms of the 25th to 75th percentiles in these boxes of the max 10-meter winds in this particular plot within 500 kilometers of the cyclone center. The C's denote the cyclone average. The open red circles are denoting the average over a set of non-cyclone cases. So the background conditions are changing with time. Sea ice is melting as part of climatological seasonal cycle that happens. And so these red circles are identifying these cases and these conditions for these cases in which non-cyclone conditions were observed. So this plot right now just shows that cyclones are a bit weaker. These are meters per second in this distribution in terms of the wind speed, but more frequent as the summer progresses. So this plot now summarizes the relationship in this reanalysis data set between Arctic cyclones and the short-term changes in sea ice. So this is the percent change in sea ice cover by month, May, June, July, August on the x-axis. So negative values on the y-axis imply decreased sea ice cover. Positive values are increased sea ice cover. And you can see these non-cyclone statistics are computed with and denoted by these open circles, as I mentioned. We also have 3 different lag times here: 1 day, 3 days, and 5 days in the blue, purple, and red colors, respectively. Now you can see, starting out in the May time period, overall, May and June cyclones are actually associated with less 1 to 5 day loss of local sea ice cover than the non-cyclones. So you can see the non-cyclones actually have more sea ice loss. So we were somewhat surprised by this, but we will delve into this a bit more. And then if you go further into the summer, in the July-August timeframe, it's a bit of a mix. I mean, there are cases and certainly really long tails associated with the cyclone cases. Certainly some extreme events occur. But at the same time, in the sort of mean, the strong summer cyclones have a relatively small average effect on sea ice. So it's these extreme events that seem to be popping out, and in the sort of the mean, not so clear. Now let's take a look at this issue about the early summer cyclones and this interesting result. So we've taken a close look at the energy budget. So this is actually the surface energy flux differences between the cyclone and the non-cyclone conditions. So this is cyclone minus non-cyclone. And so the y-axis is in watts per meter squared. It's flux values. Positive values show that the cyclones increase the flux and negative decrease the flux. The black symbols are the total flux difference, and we'll go through the different components. The yellow is short wave, red long wave, blue the sensible heat flux at the surface, and green the latent heat flux at the surface. So we see early in the summer, let's take May for example, we could see that there's likely reduced ice loss from early summer cyclones that we found is associated with this shortwave net radiation that we see. So the blocking of the shortwave by the clouds associated with the cyclones are leading to a decrease in the flux by the cyclones and actually slowing the sea ice loss during this period. If we shift to August, you can see it's quite a dramatic difference in terms of the energy balance. And in August, cyclones have a relatively smaller effect on the surface energy budget compared to other months. You can see still a signature of the shortwave radiation, but now the sun, of course, is not as high in the sky in August in the Arctic, and so it doesn't quite have as big of an effect. We can see the other components are relatively neutral, so it's a bit of a smaller effect overall. There's some boxes that popped on, drawing our attention to that shortwave net radiation and those differences between the cyclone and non-cyclone conditions. So we'll continue to take a closer look at that. And so here we take a closer look at the shortwave forcing and looking at the cases of cyclones versus non-cyclone events. So cyclones reduce the net shortwave within the marginal ice zone where the sea ice edge typically retreats faster in May and June. So these are maps of differences in the average net shortwave flux between the cyclone and non-cyclone cases in May and June in the Atlantic and the Pacific sectors. The thick black line indicates the 80% average sea ice concentration contour. The black stippling indicates where the cyclones increase the cloud fraction in the mid to low levels. The cyan contours, this light blue, stippling indicates where the cyclones decrease the cloud fraction in the mid to low levels. These orange dots are the cyclone locations and intensities similar to what we saw before, and we've averaged over 24 hours. So the reduced shortwave net radiation coincides with where cyclones increase the mid and low level cloud fraction by more than 15%. This is the black stippling. So you can see the blue shading where the differences in the net shortwave are negative. You can see lots of this black stippling associated with the clouds and the cyclones. So the cyclone clouds, we've hypothesized, prevent the strongest solar radiation of the year from being absorbed in the marginal ice zone. So it's a very important time of the year in the Arctic for melting, and this slows the process actually out in the early summer, slows it down. So recently, been working with Pete on some new metrics of cyclone surface wind forcing, and Pete has come up with some interesting ideas on this. So we want to quantify the advective effects of cyclone winds along the sea ice edge using the ERA 5, the same reanalysis data set. And we want to account for wind speed and direction relative to the local ice edge. And so what we've come up with here is expressing basically a V cross wind component. So this is a cross ice edge wind component, and it's a projection of the local 10-meter wind vector on the maximum sea ice concentration gradient. And this just shows or illustrates a couple of these examples of where that gradient is negative, where the 10-meter wind vector in red is opposite from the ice concentration gradient vector. And if it's in the same direction, it's greater than 0. So it's positive, basically, when wind blows towards the ice edge, which actually, if you think about it, locally reduces the ice edge concentration via ice advection. So this is a negative correlation between what's happening with the ice and the winds, and this V cross component. So now we're going to take a closer look at this, and we're going to look at the relationship to sea ice change. And we're using correlation coefficients that show the extent to which the wind-induced ice edge or ice advection explains local changes in the sea ice area. And we stratify this by, Pete does this by May, June, July, and August. And you'll have to remember that there's some differences as in terms of the cyclone locations as we go through the year. So in May and June, we tend to be more in the Atlantic sector before shifting more towards Siberia and Alaska in July and August. The redder colors denote timescales for which the wind-driven advection reduces sea ice cover around cyclones. So let me explain this a bit more. So these two different axes, if we increase along the y-axis, this is a longer change in terms of the ice lag. And then on the y-axis is averaging of the winds centered on the cyclone. So moving to the right along the x-axis is longer averages for the winds. So in May, we have basically a period of pretty rapid response in terms of the sea ice. We don't see much of a lag in terms of the wind average, and we are getting a fairly rapid change in the sea ice based on the winds. So there's not much of a lag, and this is an immediate response likely associated with, we hypothesize, advection of the ice itself by the cyclone. If we look at July and August, we see quite a bit more of a lag in these months. And these time average winds really are pointing towards longer term changes in the sea ice extent. This is a lagged response that we think is likely due to more complex processes. As we saw in the initial part of this with the coupled model, we saw that the ocean can be very important in the melt process, and we think this is pointing to subsurface ocean mixing processes that may be enhancing the melting. So this is underscoring the very interesting differences between the early part of the season in terms of the melt season starting in May, contrasting that with what's going on in the July and August later in the season in terms of the cyclones and how they impact the sea ice. Now we're going to take a look closer at a couple cyclone examples. One of them is an especially intense cyclone that occurred in August 2016. We are going to, here we're looking at, we're computing V cross at each point within a box, enclosing the region that is strongly affected by the cyclone wind radiative forcing. So we're concentrating our analysis in that box, and we're looking at scatter diagrams that show the sea ice change concentration over 1, 3, and 5 day lag times across the in the X direction here. We have 2 different panels here. One of them is ice concentration, change in ice concentration versus this V cross wind component. So it's the winds. And the second one, it's the change in ice concentration versus the energy budget, the net energy budget. You can see just broadly in this scatter plot that the wind advection has a stronger relationship to local changes in the sea ice concentration on these relatively short timescales relative to the fluxes. So the net flux doesn't quite have as strong of a correlation. And this is interesting. It may be happening, there may be more complicated processes going on. And there certainly are in terms of air-ocean ice coupling. And it underscores the different timescales, perhaps, that wind-driven advection and some of these fluxes are responding. If we take a look at this second case now, similar setup. This is now the Great Arctic Cyclone of August 2012 that we looked at with the coupled model. We're looking at, once again, on the top panels, the change in sea ice concentration versus the V cross wind component. And you can see, once again, fairly nice scatter and correlations between the changes in ice concentration and this and the wind-driven advection. The energy, once again, doesn't really correlate as well. It explains a really small fraction of sea ice change. So I think overall, the wind-driven advection and energy flux suggest other ocean-related processes that I mentioned earlier that may be accelerating sea ice loss associated with turbulent mixing in the ocean and release of the warm water from some of these barrier layers that seem to be important in the Arctic. Now shift to the last topic is Arctic cyclones and the relationship to moisture transport. So this is some work that's been led by Matt Fearon. And there are, of course, a lot of previous work that's been done that has highlighted the importance of moisture in the Arctic and how this happens. It can occur in response to regional cyclone activity or mid-latitude flow amplification. For example, Rossby wave breaking, many studies have highlighted that. Transport episodes are characteristically described as moist intrusions of high moist enthalpy that are ejected poleward of 70 north. There's been several studies noting that. And these moist intrusions have important implications for clouds, Arctic warming, and sea ice melt in general. So understanding the nature of moisture transport into the Arctic is really important for understanding the overall energy cycle in the Arctic and the overall budgets. So Matt's done a lot of work with the reanalysis, and he's done some very careful diagnostic calculations. One of the things we've looked at is quantifying the relationship between cyclones and moist intrusions. So this is an example of the algorithm that was developed. And first of all, the black contours show sea level pressure with yellow dots showing intensifying cyclone centers. You see a couple of these dots denoting cyclones. Here's another one. The shaded region of integrated vapor transport within the red contours, so you see these solid red contours, indicate the cyclone-induced moist intrusions. So there's a relationship threshold that is needed to be satisfied between the intrusions themselves and the existence of a cyclone. Then these linear yellow segments indicate the poleward extent of that moist intrusion as it crosses 70 north at a particular time. So we are spending time here computing the fluxes of moisture associated with these intrusions as they move into the Arctic and have some connection and reason for their existence associated with these cyclones, oftentimes occurring in warm sectors of cyclones. So we performed a nice seasonal climatology of cyclones and moist intrusions, looking at the different seasons. And these are counts of cyclones that were performed using the ERA 5 reanalysis data set, and also Michael Sprenger's of ETH, his cyclone data set that he has based on the reanalyses. And so we could see different regions become more active in terms of cyclones as we move into spring and summer. We start to see this region along the Siberian coast become much more active, and then in autumn retreating back into the Atlantic sector, which featured in the winter and spring. We see somewhat of a similar story with the moist intrusions. We see this Atlantic sector. We see a lot of the intrusions concentrating in this Atlantic sector for winter and spring, and we see to some degree autumn. And we see in the summer multiple intrusion corridors, especially that occur from continental regions over Eurasia, and over the central Arctic Ocean as well, that occur in these cyan shading regions. So this summertime period is actually a very interesting time. It's of course when the melt's occurring, but also some real interesting anomalies occur during the summer associated with the cyclones themselves and these moist intrusions. So the nature of how the pathways of which moisture get into the Arctic are very different. Okay, so, oops, we have a couple of things popping on. So I wanted to say also that this is a very important statistic that cyclones account for a remarkable almost 75% of the annual moisture transport into the Arctic associated with these intrusions, and 81% in the summer on average. This is a remarkable number and just underscores how important these cyclones are to the overall transport of synoptic and mesoscale moisture into the Arctic. So next we'll look a little bit more at some of the source regions. So one of the capabilities that Matt's been able to build in with some of our analysis tools is performing trajectory analyses. So back trajectories were computed from 70 north, so they're initiated at 70 north within these moist intrusions over a 2 to 5 day period. We can see these different source regions in the different seasons, and especially paying attention here to summer since we're most interested in that. We can see that the source region counts are greatest overall in the summer and found most frequently over the high latitude continental regions of Eurasia. So this looks like a very important source region that are driving a lot of the moisture transport into the Arctic in the summer. And furthermore, if we look at the monthly average latent heat flux now, and looking at July as an example, we see there's month-to-month increase in the latent heat flux as we approach midsummer, and that's over these uptake regions over the continents where we saw the source regions associated with the back trajectories. See a July maximum. And so this these trajectories originate oftentimes in the boundary layer, just above the boundary layer in the reanalysis, and are close to these areas where the latent heat flux can be transported in the vertical. And these end up being important sources as these moist intrusions and cyclones move into the Arctic. It's just highlighting that region of especially large latent heat flux during the July time period. Now, if we take a look at a cyclone example, and we're using the Navy's mesoscale modeling system called COAMPS, and it's applied here at a 15-kilometer horizontal resolution with the NOAA land surface model. We use 4 soil layers in the surface, or the soil model. And this just shows the color is the top layer soil moisture fraction in the 0 to 10 centimeter range. And you can see quite a lot of differences across Eurasia, but in these source regions, you can see it's actually quite moist. The cyclone path is shown in magenta. We're also taking a look at this August 2016 cyclone that we looked at earlier in Pete's analysis with the scatter plots. So these show, first of all, in black, this is the evolution of the central pressure versus forecast hour. We could see the cyclone develops to a very intense cyclone in the 978 range central pressure in this time period. The cyclone was thought to have an important impact on sea ice reduction. 2 different experiments were run, reducing the soil moisture by 50%, and a second one reducing it to 0. And you can see the resultant central pressures of these simulations in the red line and the orange line from those 2 experiments. So that has a pretty big impact on the cyclone, but it still is a relatively strong cyclone. So here we show more back trajectories. So these trajectories are initiated in the moist plume and taken from a zone east of the cyclone. And these are now shaded by mixing ratio in the blue colors. And the darkest blue are the largest value of mixing ratio concentration, so the water vapor concentration. The lighter gray and to white indicate drier. These are the 3 experiments. And we look at the control. We could see that a lot of these trajectories, first of all, they begin a lot of times near the surface. They get moistened as they propagate along the near the boundary layer and just above the boundary layer, and then are lifted into the moist intrusion. And looking at the 2 experiments, reducing the soil moisture by 50% and then reducing it to 0 has a dramatic impact on the moisture content that feed into that moist intrusion. You can also see in these contours, these are a few contours of sea level pressure showing the cyclone in its track. You can see the cyclone intensity has been reduced quite a bit as well. So it's important for not only the magnitude of the moisture and the intrusion, but also the cyclone too. Next, we take a look at a cross section through those intrusions for these 3 tests. And we can see, first of all, these are 3 cross sections of mixing ratio, pressure on the y-axis up to 500 millibars, 600 millibars, sorry. And the concentration or the water vapor mixing ratio shown here is obviously quite moist, below 850 millibars in the control. And you can see it's dramatically drier, although still quite a bit of moisture, but dramatically drier in these cases where the moisture flux was reduced, or where the soil moisture was reduced. And I wanted to point out, I forgot to note this, that the soil moisture was only reduced in this box region. So we're only reducing it where those trajectories and source regions are located over. So it has a dramatic effect in terms of this moist plume and associated with the moisture that goes into the Arctic. So I just want to note that we have a field program that's planned actually for this August, as long as all the pandemic is being mitigated and continues to get mitigated, and hopefully better things this summer, and we hope this will happen. And this is in collaboration with the French team, the Saphir Falcon, and it's coordinated with a UK group, John Methven and his group at University of Reading, Ian Renfrew, using the BAS Twin Otter. And there's some really nice instrumentation on the Falcon. Has a high spectral resolution Doppler LiDAR, a cloud radar, has some other nice instrumentation that are targeted at clouds. And we're working with Gwendal Riviere and Julien Delano in France, and they are spearheading this program. And there are some really nice products that come out of this system in terms of clouds and precipitation and microphysics and dynamics as well. So we're looking forward to getting some more data flying above cyclones and in cyclones, and being able to diagnose more some of the processes, not only in the low levels associated with this Twin Otter, but also in the upper levels as well. So we have a team of about a dozen scientists associated with the ONR initiative that we're working with, and we're in the process of planning our operations for this summer. So let me summarize and wrap up. So we saw that melting of sea ice can be substantially enhanced by intense cyclones. For example, the August 2012 case, the melting occurs through turbulent mixing of warm water from below and sensible heating from above. We took a look at, in terms of the reanalyses, based on a large sample of Arctic summer cyclones that are located near the sea ice edge. We see in the early summers, the cyclones act to slow the ice loss associated with clouds that block solar insolation. And then we see it's more of a complicated story later in the summer. Advection by the cyclone winds seems to have a moderate relationship to sea ice on changes of 1 to 10 day timescales, but there's still a large fraction of variance in the sea ice change that remains unexplained. It may be associated with some of these coupled processes. We saw, in terms of the importance of the cyclones and their moisture transport to the Arctic, nearly 3/4 of annual moisture transport takes place through these cyclones and their associated moist intrusions. We also see a remarkable amount of moisture over the interior Eurasia, right over the land surface, is a key moisture source for the poleward vapor flux, which looks very interesting. So I will comment that the impact of the summer Arctic cyclones on sea ice loss really remains complex and uncertain. There are offsetting physical effects. There are representativeness issues of these extreme cases. And then there's model and remote sensing errors and uncertainties that we need to consider. So it's a really hard problem we're finding, really complicated, but super interesting. We're hoping that this thin ice campaign in August 2021 will provide some much needed new observations of cyclones. And we also want to note, and from a broader perspective, that Arctic cyclones are an important and complex component of sea ice variability and have important implications across timescales from subseasonal to climate as well. So I'll stop there. Happy to take questions. Thank you very much for your interest and for coming today.
Wonderful. Well, thank you, Jim, for a great presentation on the influence of Arctic cyclones on sea ice change and moisture transport. That was a lot of rich analysis that you provided, you and your colleagues have provided. We have time for questions. Again, please use the Slido interface below the presentation screen to ask your question. We have a question from Alice D. Jim. In the early season, you suggest that on its own thermodynamics will decrease ice loss, i.e. reduce top melt, while later in the summer, the impact is small. Have you looked at dynamic impact, example, breaking flows?
Yeah, this is a great question. And I feel like we're just scratching the surface on some of these coupled processes. And I know some of our colleagues, Ola Persson, for example, has commented about the possible importance of some of the wind stress on the ice. So we haven't really delved as much into some of the ice processes yet. And I think this is a good suggestion. And we have colleagues that we're working with on the coupled system that would like to be able to look at that closer. But certainly that's a really good suggestion.
Great. Thank you, Alice D. I believe we have a question from Jürgen Jensen at EOL. What is the requirement for a cyclone to be considered an Arctic cyclone?
Yeah, hi, Jan. That's a great question. We actually talked about this quite a bit, and we have a fairly loose definition, and our interest begins when the Arctic cyclones are less than 1,000 millibars in terms of central pressure. We haven't been, so we do have a cyclone tracking algorithm that I didn't really talk about much that Michael Sprenger has that has some rigorous criteria for tracking the cyclones. And we've used that tracking algorithm to really define these cyclones and without going into details about what these different criteria are. They need to exist, for example, in the reanalysis that we've done for at least 48 hours for some of our analysis that we've done, but it also has criteria associated with its track and structure and so on. So there are some criteria. And so we've used Michael Sprenger's of ETH, his cyclone tracking data set, which is one of the ones that are used as a community standard for that. Thanks for that question.
Thank you, Jürgen. And I believe we have another question from Jürgen. Why is the Northern Eurasia the main source region for moisture intrusions in summer? Also strong over Western Europe, but not so much over Alaska. Why not Alaska? Northern Greenland may stay cool, but Alaska should have lots of evaporation.
Yeah, that's a really good question, Jan. I really appreciate that. We haven't really. I don't have a strong explanation for that right now, other than that the climatological nature of the cyclonic activity that we've looked at in the reanalysis shows that the Siberia region and the Siberian coast tends to become really active. And it's not saying that we don't get cyclones along the Alaska coast in that region. It certainly is active in the latter part of the summer, but just not quite as active in terms of the synoptic and sort of the Arctic wide scale dynamics that are driving some of this cyclonic activity. So I'm not really sure I have a good answer for that, but I think it's an interesting question.
Thank you, Jürgen. We have a question from Jimmy Dudhia. I apologize if I don't pronounce your name correctly. This person asks, do the models have ice advection?
That's a good question. In the community SICE model, I believe it does have ice advection in it, but I would have to check more into the details in terms of what's being done. And I'm not that familiar with that end of things, but I believe it does. It's a pretty sophisticated model in terms of processes. So I will check and get back to you, Jimmy. Thanks for that question.
Great, thank you, Jimmy. We have a question from Wayne. He asks, the area of interior Eurasia that provides the moisture is also a source of pollutants. Will you be able to learn anything about particulate pollution, for example, aircraft observations?
Yeah, that's a great question. I hadn't thought about that angle, but I think that's a very interesting point. Our aircraft that we're collaborating with the French it does have capabilities in terms of aerosols. And so there may be some measurements that may shed some light on that. On the challenging side is that, of course, some of the most interesting transport related to the pollutants into the Arctic are going to be happening north of Siberia in the Russian airspace sector that we won't be able to fly in. So I'm not sure how much we'll be able to get into some of those, but that would be quite interesting, I think, and something we'll have to do some more analysis on. I think it is an interesting opportunity. So thanks for that. Agreed.
Great question. We have a thank you, Jim. Wonderful presentation from Stephen Bussinger, I believe. So thank you, Jim, for a wonderful presentation. I believe we have another question.
Thanks for that, Steve.
Maybe answers Jimmy's question. Alice D says, CICE has advection. It's a fully dynamic thermodynamic model with an ice thickness distribution as well. Thank you, Alice.
Thanks for that clarification. I appreciate that. I'm not an expert on the SICE model for sure.
I have a question, Jim, that sort of speaks from sort of the other end. So as sea ice loss continues in response to these intense cyclones and other factors, how will that in turn change the cyclones themselves?
Yeah, that's a great question. there, there are a number of different facets I could think of that, the changing Arctic, of course, having less sea ice extent certainly may change some of the impacts depending on the climatological locations of the cyclones, for example. I think one of the biggest effects are the thinning of the sea ice that we see, and the fact that the cyclones may be able to have a different impact as the sea ice thins and the climate changes. So that's possible. In terms of feedbacks in the summer, so there presumably will be more open water, and this can have more of a different effect on the cyclones themselves. We see typically in the summer that the surface transport in terms of heat and moisture from the surface are relatively small. The air-sea temperature difference isn't very large, unlike in the winter sometimes where the cold air spills out over the open ocean. But nevertheless, the greater open water certainly could be changing the characteristics of the cyclones, and maybe more importantly, what's happening below the surface in the ocean. And just the fact that more open water may lead to more wave and turbulent action that may mix the ocean and change properties also. And so that may be an interesting side factor as well. And I don't completely understand the types of feedbacks that could be occurring, but certainly that's something that is definitely scientifically worth exploring as we kind of peel back the layers on all the complexities of these cyclones and also just the couple processes in the Arctic. But thanks for that question.
Had to end on a high note, hey, Jim.
Right.
Well, we are at the end of the seminar hour. If you are interested in Jim's research and have further questions, please reach out to Dr. Doyle via his email, which is provided on the seminar flyer. On behalf of EOL and M-Cubed, I would like to thank you, Dr. Jim Doyle, on your excellent and informative presentation in the realm of Arctic meteorology. Thank you, everyone, and have a great day.
Thanks again for inviting me. Thanks to everyone who attended. Thanks for all your interest. It was great fun for me to present. It would have been even better to be there in person, but it's great to be able to do this virtually in the middle of the pandemic. So I really appreciate that. And so thanks to everyone again, and hope all of you have a great rest of your day.